Hi everybody, I would just like to show you another video on position time graphs, velocity time graphs, and also this notion of average velocity versus instantaneous velocity. This will piggyback kind of nicely onto the last video that we made. Just recall, whenever we say velocity, in general, we're talking about how steep the position versus time graph is. That was our original definition of velocity. Now, for an object that's moving steadily, it's really easy to do that. It's easy to see what its slope is, but for an object like this, which began at rest and then sped up as time goes along, that's a little bit harder to do. Velocity tells you two things. It tells you how fast an object is moving, so that's like the number that goes with the velocity, and also what way the object is moving, its direction. And typically that's denoted with a positive or a negative value. Positive would mean moving to the right, negative would mean moving to the left, something like that. For an object whose velocity is changing, we introduced this idea of an instantaneous velocity. So, for instance, at 2 seconds, how fast is the thing going and what way? And I had told you in the last video that, without using a branch of math called calculus, it's hard to put an exact value on that from a graph like this. But we had kind of come up with a shortcut, a way around this, a workaround, if you will. If I want to know how fast the object is going at 2 seconds, we said, all right, well, why don't we look at the small interval from right before to right after, and we'll figure out the average velocity over this short interval and call that the instantaneous velocity at 2 seconds. So I would do like change in position from 1 to 3 seconds. And I would divide that by the change in time, which is 2 seconds. And I would end up getting velocity values from that. And that's exactly what I did down here, and I plotted this graph. This is just like the last video. Well, I want to kind of revisit this notion of average velocity, because not only does it apply to a graph that looks like this, you can also figure out an object's average velocity from looking at this. This graph tells you how fast the thing is going at any given point in time, but you can also speak in terms of averages. So let's go back to what we know here. Average velocity, v bar, is equal to displacement over time. That's our current kind of notion of this. So if I wanted to figure out the average velocity for this whole motion from 0 to 6 seconds, I could simply imagine that I'm drawing a line right there and I'm finding the slope of that line. I'm taking this motion, which began actually at rest, sped up, sped up, sped up, and then started going fast, 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 and I'm kind of turning it into an average steady motion over the whole 6 seconds. So my average velocity would be change in position, that's 18 meters minus 0 meters, so that's an 18 meter displacement, and that happens in a time of 6 minus 0, 6 seconds. All this is saying is, on average, this thing went 3 meters for every second. Granted, at the beginning, the thing had a speed or a velocity much lower than 3 meters per second. It began at rest. By the end, it was probably going a lot faster than 3 meters per second. In fact, it was going 6 meters per second at 6 seconds, according to this graph. So the only time this thing had an actual velocity that matched up with its average velocity was right in the middle, which is sort of what you would expect. Now, how could I figure out this average velocity, not from that graph, but from this one? Well, you guys know how to average numbers, so here's another way to look at average velocity. If I simply take the average of the initial velocity and the final velocity, like literally average those two numbers, let's see what we get. You guys know to average things, you have to add them up and divide by how many things you added. So if I take the initial velocity, the final velocity, add them up and divide by 2, what do I get here? Well, V initial was 0 meters per second. V final is 6 meters per second. Divide by 2. Holy smokes. You get the exact same thing. This is literally called the average velocity rule. So I have two ways now of thinking about average velocity. One that relates displacement and time, and one that relates initial and final velocity. And they can be used sort of interchangeably. So if I only had, forget I even had that. If I only had this velocity versus time graph, it would be really easy to figure out how far the thing went. I would simply find my average velocity and use the fact that this is still legitimate up here. That average velocity is equal to the displacement over the time. Therefore, the displacement would be equal to the average velocity times the time. So let's look at how this would work. Let's see if it returns the right value for displacement. My average velocity, v bar, we just said is 3 meters per second. And the time, this was a 6-second time interval. So according to this, my displacement using the average velocity rule should be 18 meters, which if you look back up here, the thing indeed had gone 18 meters by the time it hit 6 seconds. This is a really handy idea. It takes a complicated motion, like accelerated motion, and turns it into a more simple one. Now this line represents the instantaneous velocity of the object. If I were to simply show the average velocity of this object with a different line, here's what it would look like. There's v bar, the average velocity. So notice, if you go back to our idea that we've used in the past that the area under a velocity graph represents displacement, let's look at why using the average velocity and using the instantaneous velocity would give you the same result for how far the thing went. The instantaneous velocity, if I were to find the area under that, it would be the area of this big old triangle. That area would represent how far the thing had gone, displacement. Well, using the average velocity, I'm talking about the area of this rectangle. You guys are probably pretty familiar with shapes. Imagine if I were to just chop off this part right here and flop it over, it would be the exact same area as this rectangle. So this stuff with using the average velocity is going to give you the same thing as using the actual velocity when it comes to figuring out displacement, how far an object has gone. It's a neat way to relate them rather simply. I can give you some more examples. Just a couple more. So, graph number 1 says find the displacement of the object over the interval from 0 to 6 seconds, first using the area under the velocity graph. So let's look here. This is an object that had a positive 12 meter per second velocity. So it was moving forward to the right at 12 meters per second. And over 6 seconds, slowed to a rest. So if I want to get the area under this, that's the area of this big old triangle. The displacement would be the area, so that would be 1/2. This thing has a 6-second base and a 12 meter per second height. 1/2 base times height. So 6 times 12 is 72 divided by 2. This gives me 36, and check the units out, meters. So that should be how far this thing went over the 6 seconds while it slowed down from 12 down to 0 gradually. Well, it might be simpler to just say, all right, well, this thing started going 12 meters per second and ended going 0 meters per second. What was its average velocity? So the average velocity for this motion would be literally the average of the initial and final. So that would be 12 meters per second plus 0 meters per second. Divide them by 2. V bar equals 6 meters per second. Now, this thing was only actually going 6 meters per second at one moment in time, at 3 seconds. Up until then, it was going faster than 6 meters per second. After that, it was going slower than 6 meters per second. But on average, it was going 6 meters per second. So using this, the displacement would be the average of 6 meters per second times the 6 seconds that it went for. Notice you get the exact same thing. So 36 meter displacement, 36 meter displacement. Now in that case, it wasn't terribly hard to just do the triangle, but as things get more complicated, this idea of an average velocity becomes easier and easier to use. Let's take this for instance. Graph number 2, find the displacement of the object over the interval from 0 to 5 seconds. So this thing already began in motion. V initial is 5 meters per second. V final is 15 meters per second. So it began moving to the right at 5, sped up 5 seconds later, it's going 15 meters per second to the right. How far did it go? Well, the displacement is going to be the area beneath the graph. Now, this is kind of a funky shape. It's a trapezoid, but I'm going to simplify it and say, hey, it's actually a rectangle with a triangle sitting on top of it. So its displacement would be the area of the rectangle plus the area of the triangle that sits above. Now let's look at how big each of these are. The rectangle is 5 seconds long times 5 meters per second high. Add to that the area of this triangle. 1/2, its base is 5 seconds. Its height is, it's not 15 tall, it's 10 tall, from 5 to 15. 10 meters per second. Let's find the sum here. 5 times 5 is 25. The units would be meters. Oops, 25 meters. Plus 5 times 10 would be 50. The units would be meters. Half of that is 25 meters. So in actuality, this thing went 50 meters. That was its displacement over the 5 seconds. That was kind of complicated though. Would this simplify things? What was its velocity on average? Well, this thing's velocity on average, V bar, equals what? Initial velocity was. Final velocity was 15 meters per second over 2. On average, this thing went 5 plus 15 is 20, divided by 2, 10 meters per second. Makes sense. If you start going 5 and you end going 15, you probably went on average 10. So this thing's displacement must have been that average velocity times how long it went that average velocity for. Average velocity is 10 meters per second. And the time was 5 seconds. 10 meters per second times 5 seconds. 50 meters. What do you know? You get the same thing. So here it was probably more advantageous to do this. It was pretty easy up there to just use the actual area under the graph to figure displacement. But as things get more complicated, this becomes a more useful idea. Hopefully this helps. And to kind of summarize, you've got two ways, folks, to think about average velocity now. One is relating displacement in time, and the other is relating initial and final velocity. And this is called the average velocity rule.